Today we're going to take a look at apportionment and the Hamilton method for apportionment. First of all, in apportionment, it is technically a subset of fair division, which is what we did in the last unit, but in this case, all of the objects are the same, but the players are entitled to a different number of objects or different size shares. So some examples. The main one that we're going to be focusing on is assigning the seats in Congress according to a state's population. Some other examples are scheduling nurses to different shifts in a hospital, scheduling subway cars to routes in a subway system, or giving candy to children based on how many chores they did. So, first we have some general vocabulary. We are going to use the word states to describe the players involved in the apportionment. Now, these aren't always actually states. In the previous examples here, these would be the shifts in the hospital, the routes in the subway system, or the kids who did the chores. And we're going to say that there are N states. The seats are going to be identical, indivisible objects. Indivisible meaning you can't have half of a seat. And these objects are being divided among the states. So in these situations up here, obviously the first one, the seats are actually the seats in Congress. And the other examples, they would be the nurses, the subway cars, or the candy. And we are going to say that there are M seats. The population is the total weight used to distribute seats to the states. And we're going to call that P. Now, we do have some more mathy vocabulary that we need to talk about. First is truncating. Truncating means you basically ignore the decimal part of a number. So 5.2, if you truncate it, would just be 5. We have the standard divisor, which we are going to abbreviate as SD. That is the ratio of the population to seats. So for every, whatever your standard divisor is, that number of people, each state is entitled to 1 seat. The way we find the standard divisor is by taking the total population and dividing by the total number of seats, or P divided by M. The standard quota is the exact number of seats, including the decimal, that a state would get if they could get a fraction of a seat. So to find the standard quota, you take the state's population and divide by the standard divisor. Then we have the upper and lower quotas. The lower quota, you just take the standard quota and round down. The upper quota, you take the standard quota and round up. If the standard quota is a whole number, then the upper and lower quotas will be the same. So let's look at that part of the example. We'll get into a more complicated example in a minute. So if our standard quota is 32.92, our lower quota, you round down, is going to be 32. The upper quota, if you round up, is 33. That's it. So if we go through this chart, for the standard quota of 100.12, our lower quota is 100, our upper quota is 101. For 54, since that's a whole number, both the upper and lower quota are going to be the same because there is no decimal, so we can't round it. If your standard quota is 50.5, the lower quota is 50, upper quota is 51. If your standard quota is 99.99, your lower quota is 99, your upper quota is 100. And if your standard quota is 0.8, your lower quota is 0, your upper quota is 1. Now, let's look at a longer example. Bogus High School has sophomore, junior, and senior classes of 464, 240, and 196 respectively. Respectively means that there are 464 sophomores, 240 juniors, and 196 seniors. There are 20 seats on the school's student council, and they are divided among the 3 classes based on the population. So we have a reminder of our 2 formulas here. For the standard divisor, you take the total population of the school and divide by the number of seats. So that's the first thing we want to find, is our standard divisor. So I'm going to write out all of the work. So our total population would be 464 plus 240 plus 196, and we are dividing by the total number of seats on the student council. If you add this up, you get 900 divided by 20, which is 45. So what the standard divisor tells us is that for each group of 45 students, there should be 1 representative on the student council. So for each 45 students in the sophomore class is entitled to 1 representative on student council. So I'm going to go ahead and copy the populations down here. To find the standard quota, we want to take the population of each grade level and divide by the standard divisor, which is 45. So if you grab your calculator, do 464 divided by 45, you get 10.31, and do the same for the juniors and the seniors. So all I did to get those numbers was divide these by 45. Now, if I add these up, just to check, I get 19.99. So basically 20, but I rounded. Now, if we just rounded these numbers like normal, they would all end up rounding down. And we would only have 19 people on the student council. So the problem with conventional rounding, which is rounding like normal, is that sometimes you can get too few seats and sometimes you can get too many seats. So there are a variety of methods to deal with this rounding problem. The first one we're going to look at is Hamilton's method. So Hamilton's method is also known as the method of largest remainders, and mathematically it is the simplest of all of the methods we're going to look at. You got 4 steps. First, you find your standard divisor, then you find your standard quota for each group or each state. Then you automatically give each state the lower quota. If you add those up and you have the right number of seats, then you're done. If you don't, then you give extra seats, one at a time, to the state with the largest decimal part until you have reached the appropriate number of seats. So we're going to go back to the class council example. So I'm going to copy down some information from the previous slide, and then we can continue with this method. So on the previous slide, we had already done steps 1 and 2. We found the standard divisor, we found the standard quotas. So now I am going to assign each grade level their lower quota, which means I'm going to round all of these standard quotas down. Now, that is only 19 seats. We need one more seat. So, we are going to look at the decimal parts of the standard quota. Which grade level has the largest decimal part? Well, that would be the seniors. So the seniors are going to get an extra seat. We had 19, we needed 20, we added one extra seat, so we should be good. So the sophomores are going to keep their 10 seats, the juniors keep their 5, and the seniors got the 4 plus an extra seat. So now we are at 20 seats total. That's the Hamilton method for apportionment. Depending on how many total seats you have from the lower quotas, you might have to add more than one extra seat, and that's fine. If we needed another extra seat, the next one would go to the juniors because their decimal part is the next largest, and then you would continue in decreasing order. So, in summary, every state gets at least their lower quota. As many states as possible get the upper quota, with the state with the highest fractional or decimal part having first priority, then the state with the second highest fractional part, and so on. In general, each of these methods that we look at in this unit are biased. Hamilton's method favors large states over small states. Like we talked about when we looked at voting methods, there are a bunch of rules and a bunch of paradoxes. The first rule is the quota rule. A state's apportionment should always be either the upper or lower quota, which Hamilton's method satisfies, so it does not violate the quota rule. Now, throughout history, there have been a variety of issues with Hamilton's method. You don't need to know all of these paradoxes, but I'm just going to run through them real quick. First was the Alabama paradox. In 1880, the Congress decided to increase the total number of seats in the House of Representatives, but when they did the math, Alabama ended up losing a seat. So that's the Alabama paradox. If you increase the total number of seats, someone could end up losing a seat. In 1900, we experienced the population paradox. A state's population increases, but they lost a seat to a state whose population didn't change, or whose population didn't change as much. The third issue with Hamilton's method is the new states paradox. In 1907, Oklahoma was added to the Union. The House of Representatives was increased from 386 to 391 seats because, based on Oklahoma's population, it was entitled to 5 seats. So they redid the calculations, and somehow New York lost a seat to Maine. So the new states paradox is adding a new state to the Union can affect the number of seats that other states get. I will tell you, none of these methods for apportionment are perfect, but Congress has decided that certain issues are less severe than others.